We have talked about curl in calculus. Now we would see flux in calculus. Curl in calculus, we have talked. What is flux in calculus? If I have a vector field, if I have a vector field and if I consider line integral of the vector field along a line, then it is called line integral. If I divide the line integral, if I calculate the line integral in a closed loop and then divide by the area of the closed loop, then it is called curve. Line integral divided by the area is curve. So if I have a line integral in a closed loop from point A back to point A, then it forms a surface area of a circle. If I calculate line integral of any vector field along this line and whatever it comes, divide by area of the circle, divide by area of the circle is the curling factor. What is the tendency of this vector field to rotate something? Typically, we take force field as vector field, force vector field, and line integral of the force vector field generally it transforms into work done. So force vector field line integral is work done. Work done divided by the area. If the work done is along a closed loop, divided by the area of the closed loop is the it also called circulation density or it is called curl. Now we are in flux. Curl, flux. Say what is common here? Vector field. Vector field. So I have a vector field and what is the flux of the vector field? Generally in curl fundamental we talked about force vector field. Vector field is vector field is a algebraic vector. A vector has components I, j, k components. Each component rather than numeric, if it is algebraic function, then this vector is called vector field. Depending upon the independent variable's value, it will generate different static vectors. Somehow, people they say the vector field as a function which generates different vectors where the input to the function or parameter to the function is the independent component x, y, z. Okay, so that is a story of a vector field. That is the story of the vector field. What about flux? Earlier we talked about vector field, that was force field, mainly force field. Now we are talking about vector field. Typically it is velocity vector, flux. Okay, so consider, okay, so fundamental comes as what is a flux? What is a flux? Now consider that there is a velocity vector. What is velocity vector? Typically water flowing. If water is flowing, then it has velocity. Water is flowing, then it has force. That force vector field we talked in curve. Okay, if there is a water minus x axis to x axis it is flowing, this is y axis. Okay, okay, so consider this is y axis, this is x axis, and this is y axis, minus x2 plus x, and then y axis, x axis, y axis. If there are, it is something like this, and water is flowing from minus x side to x side, minus x side to X side. Water is flowing. If I keep an item on the water, then what item it moves through. If item moves through, this proves that there is a force in water, and because of that force, this item is moving. If item moves from here to here, the work done by the force is forced into this displacement. If water force is not in the direction of the displacement, then force vector dot displacement vector. This is what we see in the work done. So if water is flowing, there are two kind of vector field that is in discussion. One is force vector field that we use in curl or line integral. One is velocity vector that we will use in the flux calculation. So what is flux? If there is a water flowing from this direction to this direction, and consider that I have a surface. There is a circular surface. Now I am placing this surface in the direction of water. This surface is exactly perpendicular to the water. Now, if water is flowing, and then how much water flows? Now, here, consider this is a pipe. Okay. So, now, consider this now. Okay. So, this is a kind of a bottle, cylindrical bottle, and now water is flowing from here. It is entering here, and it is exiting from this. Okay. How I can say? Consider water is flowing, entering here, and it is exiting from here. Okay. Now it is empty now. Now I switched on the motor, and there is and water is flowing from here. It entering here. It is coming out of here. Consider in 1 second water came at this level only. After 1 second water came out of this. So in 1 second, how much water is what is the volume of the water that passed through this circular surface? That is the inside the volume of this bottle. Okay, bottle, can, whatever you say. So how much is the volume of a water that is crossing this surface in 1 second if it has velocity of capital F, velocity vector field? Makes sense, right? Or someone can say in this fashion also, if this is a kind of a bottle, and I have a pipe, through this pipe water is coming. The moment water enters here, and in 1 second water fills it. Beyond that it will start dropping here. But by then it is not dropping here, because it takes 1 second time to exactly fill this bottle. And beyond 1 second it will put pressure here, and finally it will come out from here. So if it takes 1 second here, then in 1 second how much water is flowing through this surface? This is the surface. So if from this surface, how much is water flowing? That is the volume of this container. This is a container. Now consider this is the surface. Consider this is a circular surface. Now with this circular surface, I have attached a pipe. There is a pipe that is attached, and water is coming. Now water is flowing. See, there is a hole, right? There's a circle, and there is a hole, and water is flowing from this hole, and it is going right side. In 1 second of time, what is the amount of the water that is flowing through this circle? This is called flux. Flux. So flux depends upon the velocity vector. Flux depends upon the area. So what is the flux? Flux of a particular vector field through this area. This is called flux. What is the net flux? Flux means what is the net amount that is passing through a particular area. So flux depends upon the velocity. Velocity is meter per second, whereas the area is meter square. If you multiply meter per second with the meter square, it becomes meter cube per second. So what is the net volume of the water per second it is flowing through this surface area, meter cube per second. So if I have a vector field, if I have a vector field capital F, and if I have a vector field capital F, and that is a velocity vector considered, then what is the flux, what is the net volume that is coming out of a particular area? That is the flux of this vector field through that area. If I don't say vector field is a velocity vector, then I can just say that vector field vector field multiplied by area, vector field multiplied by area. But someone can obstruct, right? Someone can resist. Not necessarily. If water is flowing like this, exactly perpendicular to the surface, then maximum throughput will happen. What about water is, if this is the water direction is like this, and then it is flowing through the surface. Certainly, the throughput, the output I am getting through this surface will not be forced into area, because water is flowing exactly parallel to this surface. If that is the case, then no water is entering at all. This proves that water and the surface area, their direction makes it. This is more now. Now we are entering into vector. So water, if I consider as vector field, and then vector field is an algebraic vector, and consider algebraic vector, and now consider this surface has a direction. This is oriented surface. Or we will talk what is difference in oriented surface and non-oriented surface. So typically a surface which has two sides, distinct two sides, is called orient surface. Like if I have this surface, then it has one side like this, and it has another side, this side. This side is one side, this side is one side. Consider this is a closed surface. Like this is a closed surface, there is no hole here. Then it has one side as this. Then if I rotate, then another side as this. There are two sides. Okay, so this is called typically oriented surface. There are kind of surfaces which are not oriented surfaces, where they do not have two sides. Come on, if I have a plane, then certainly it will have two sides. Not necessary. That we will see that how it's possible that we will not have two sides even though it is a plane. Okay, so oriented surface. So if I have a oriented surface, then it has a direction. So consider this as a consider this as a surface, then it has direction that is perpendicular to it. So this is the direction of the surface. Okay, so if surface is going like this, the direction is also changing. What is the direction of other part of this surface? Then other part of the surface, the direction is like this. If I go from one part of to other part of the surface, then it will cross a boundary. That's why it is oriented. One orientation to another orientation, the progress is not smooth. It will pass through a boundary where the normal is not defined. Otherwise, surface is oriented, it will have a normal vector. If surface is like this, the normal vector is like this. Oops. Okay. If surface is like this, the normal vector is like this. Normal vector will go perpendicular to the surface area. This is normal vector to the surface. Or you can say the surface direction. This is better word. What is the surface direction? Then this is the surface direction. If that is the case, then what is the flux of a vector field along this surface? If vector field is capital F, then capital F dot A vector, capital F vector dot A vector. Consider that vector. Now I am not talking about vector field. Simply talk about vector. If I talk about vector, then it is static vector. Consider the velocity of the water is 2I plus 3j. So velocity along x-axis is 2 and velocity along y-axis is 3. Net velocity is 2 square plus 3 square square. That is the velocity vector of water. Now the area vector is along x-axis. Now it has an area. The radius of this is 2 meter. So this is not 2 meter, but consider 2 meter. So radius is 2 meter. So the area of this is 2 is pi r square. Pi 4. 4 pi meter square is the area. But the vector of the surface is completely along x-axis. Now, what is the flux of this vector along this area? What is your area? Area is 4 pi I vector. What is your force? 2I plus 3j. Then it is dot product. So j will go away and 2 plus pi 4. So it is 8 pi meter cube per second is the net flux. Okay, what is the velocity of your water? That is 2 square plus 3 square root. But you are taking only 2. That is far bigger, right? 2 square plus 3 square root will come as square root of 30. So it will be around 4, but I am taking 2 only. Means I am not taking z component. So the flux, the net amount of water that is flowing the surface area where water, if this is x-axis, this is y-axis, then water direction is like this, whereas surface area direction is like this. So what is component? What is effect? What is effective water? What is the velocity of this water effective along x-axis? What is velocity of this water that is effective along y-axis? If I talk about effect, then it is 2I plus 3j. Then effective water velocity along x-axis is 2. Effective water velocity along y-axis is 3. Whereas the area orientation is only along x-axis. So y-axis factor will go up. So 2 into the area pi r square. That is again 2 meter square. So 4 pi into 2. 8 pi is the net flux or meter cube per second that is flowing through the surface. Even though the net water that is flowing from the pipe is square root of 30. If I bend this pipe fully along x-axis, then what would be the net flux would be through this surface? Then it is pi r square is the area, that is 4 pi into square root of 30. So 13 into 4 pi is the net flux that is flowing through the surface. Flux can be calculated for magnetic field. Flux can be calculated for electromagnetic field, electric field, earth gravitation, whatever. So if magnetic field is flowing, if magnetic field is flowing, then what is its flux through the surface? Okay, what is the net per second the magnetic field is flowing? Okay, or if current is flowing, then per second what is the whatever you think about it. Okay, so this is the kind of condition of flux. So we are talking about flux. So flux is nothing but capital F dot A vector. What about if the what is your velocity vector field? It is 2I plus 3j. No more it is 2I plus 3j. Now it is minus yi plus xj divided by square root of x square plus y square, or minus yj plus xy divided by x square plus y square. It is your velocity vector field, yes. Minus yi divided by x square plus y square I vector plus xy divided by x square plus y square j vector. This is my velocity vector. Now, can you tell me that what is the flux of this vector along any area. What is your area? My area is I vector. No, your area is I vector because area is flat. What about the area? Okay, this is a flat area. What about area is like this? Everywhere, can you see now? If it is flat, then I change like this. Okay, I should have brought something so that I could have changed it. Okay, anyway, okay, understandable, right? I believe this piece of paper is better. Okay, so if area is flat, then what about area is something like this? Earlier it was flat, but now area is something like this. You can say in a kind of in a if I have a sphere, okay, so if I have a sphere and I cut this sphere into two parts, then I take hemisphere. Okay, I believe it's all right. So if I take a hemisphere, so if I cut this into two halves, then I take it will be like this. So earlier the surface is like this. Now it becomes surface like this. So what is the normal? Earlier, if its surface was this is better example. Earlier the surface was like this. The normal vector, the area vector was like this. Now surface is like this. What is the area vector? Okay, everywhere area vector has different direction. Then you can say it is like a vector field because if I change xy coordinate, area vector is changing. It's vector field. So velocity vector is a vector field. Vector field means velocity vector is like this. If you change xy, then it will be like this. If you change xy, then it will be like this. Everywhere velocity is changing. Like that, area is not flat. Area vector is not in one direction if you keep changing xy. Area vector, area is like this. Everywhere area vector is would change. If that is the case, then vector field capital F dot dot a vector will d will come. It is not calculus. Algebraic, if I have algebra multiplication or dot product, then it will come to calculus. So net flux was vector dot area, vector velocity vector dot area vector. Now it turns into capital F vector, that is velocity vector field dot d, d small d, that is for integration, d area vector, capital F vector dot d area vector. This is capital F vector dot d area vector. This is the net flux. If it is integration, integration along the surface, integration along the surface. Make sense? Okay. Now I'll take one example. What is the, okay, consider I have a, consider I think I have taken it. Consider there is a water that is flowing at 2 meter per second and there is a pipe and the entry of the pipe has a radius of 2 meter. Then what is the flux? Then it is 2 meters. Since they are in same direction, the area, that area, there is a surface and water is flowing in x direction. Surface surface vector is also along x direction. So dot will be perfect multiplication. If it is 2 meter per second and surface is a circular and radius is 2 meter, then 2 meter 2 pi is 2 pi 2 square 4 pi into 2 8 meter cube per second is the flux amount that is passing through this surface into the pipe. If it is beginning of the pipe, I am talking about the surface. There is a surface, from there one pipe goes, and along the surface water is coming at 2 meter per second. It is entering the surface entry point where the radius is 2 meter. You can take in centimeter also. And then what is the flux? What is the net per net amount of volume of the water that is entering into the pipe? That is area of this pipe, pi r square, and with what is the velocity? Then it is 8 pi. 8 pi meter cube per second is the water that is entering into the pipe. Okay. What about inside this pipe? This is a well-known example. Okay. Consider this is a pipe. So in pipe, water is entering from here. Inside this pipe, I place one ellipse. Makes sense, right? If this is the pipe, inside this pipe, okay. So now inside this pipe, this is a circle. Consider this is an ellipse. An ellipse enters into the pipe, and somewhere, since it is an ellipse, then it is standing in the pipe somewhere with tilted. This is a circle. I can push through this pipe. Consider there is an ellipse. Instead of the circle, there is an ellipse. I push in the pipe, and then in the pipe, it stands in the pipe not vertically, slantly. If it stands in the pipe slantly, then it will cover the full area. Makes sense, right? If it is a circle and it goes inside this pipe, then along the pipe vertically it will stand there. It will obstruct the water. But if it is an ellipse and it goes in a pipe and it rests in a pipe in a little slant way, then it will cover the pipe. Okay. Now consider the area of the ellipse is 4 pi by cos theta. The area of the ellipse is 4 pi cos theta, where it is making theta angle with the if this is the surface through which if this is the surface through which water is entering, the normal vector is this direction. Now ellipse is tilted here. if ellipse is if ellipse is tilted in the pipe, then ellipse has direction as like this, whereas pipe direction is like, it makes theta angle. If ellipse is like this in the pipe, then ellipse the ellipse orientation is along the pipe. Both are along x-axis, but ellipse is tilted. Then ellipse, the direction is area direction is like this, whereas pipe direction is like, it makes theta angle. Whatever theta is, the area of this ellipse is 4 pi by cos theta. So what is the net flux that is passing through the ellipse? Since its direction is not in the direction of water, theta. So whatever the direction of the water into this area of ellipse, cos theta, dot product. So 2 into 4 pi divided by cos theta gone, same 8 pi. So same is the kind of flux that will pass through. I can take another example. Now consider the velocity vector field, or vector field is minus yi plus xj divided by x square plus y square. If that is the formula, minus yi plus xj divided by x square plus y square, this is typically for, if I have xy plane, consider this as xy plane. This is xy plane. Then minus yi plus xj is something like, it will, if this is x-axis, this is y-axis, and this is xy plane, then this is z axis. If that is the case, then typically it will rotate like this in a circular way. That is the vector field. Minus yi plus xj means if y is 0, x-axis, then it is xj. So on x-axis, it will be like this. yi minus yi plus xj, when x is 0, then it is minus yi. Okay. So then on y-axis, it is like this. So here it is like this, here it is like this. So it is flowing circularly. This is vector field minus yi plus xj divided by x square plus y square. Now this proves that the vector field is on xy plane. If this is the xy plane, then vector field is on xy plane. If you go along z axis, the vector field will be like this only. Okay, so everywhere it is around the z axis. No, it won't change. If you go in along z direction, it won't change because it is not dependent upon k. It is minus yi plus xj divided by x square plus y square. Now question arises is, what is the flux? What is its flux along a plane that is standing on x-axis? Can you see? X-axis like this, and it is facing y-axis. So this plane, what we are seeing, it is standing on x-axis and it is facing y-axis. So its direction is j vector. Okay, and this plane is how big it is? That is 0 to 1 in x-axis, and it is on along z-axis. It is 0 to 1. It is a square. So vector field is going like this. Okay, and plane is like this. So certainly it is crossing the plane. If this is the plane and vector field is like this, then it is crossing the plane area. It is intersecting the plane area. What is the flux that is passing through the plane? That is the question. Now, what is a flux formula? Capital F dot dA vector. Capital F dot dA vector, integration along the surface. Now dA vector, dA, dA, dA is the area vector. Now here the area vector is dx dz. If I take any small strip along the surface, then this small strip has area as dx dz, or delta x delta z j direction, because it is in along the j direction, x axis, y axis, z axis. If plane is standing on x axis and it is facing y axis, then it is delta x delta x delta z I vector, delta x delta z j vector. And what is the equation of the vector field is? That is minus yi plus xj divided by x square plus y square dot dA vector, that is dx dz j vector. So first minus yi gone with the dot product. Now it remains is xy square root of x square plus y square dx dz, where x is from 0 to 1, z is from 0 to 1. So now what is y? It is standing at on x axis. So y is 0. So x by x square, 1 by x, integration of 1 by x dx dz. So 1 by x integration is natural log, that is ln x. Now ln x 0 to 1. So ln 1 minus ln 0 into dz, that is z 0 to 1, that is 1 1. So nothing. So the net flux is ln 1 minus ln 0. So whatever is ln 1, go and compute, and whatever is ln 0, go and compute. So that is the flux if a plane is standing on x axis from the origin. If this is the origin along the x axis and facing y axis, this is y axis, this is x axis, top is z axis, and vector field is minus yi plus xj divided by x square plus y square, and this surface is from 0 to 1 along x-axis and along z-axis 0 to 1. The net flux, net amount, if we consider as water, the net water that is passing through this surface is ln1 minus ln0. Okay, so we will proceed in it and we will prove it also. We have done a lot of things in while calculating the curl that came as Stokes theorem. But anyway, we will prove here also. And then we will proceed in Cartesian, spherical and cylindrical coordinate system. Those things we will proceed.